Good morning and welcome to day 5 with Focus on Energy. After the panelists' presentations and virtual networking / poster sessions, the moderators, Dr. Tian, Dr. Zenyuk, and Dr. Ahmed are planning to host 3 breakout sessions at 1 p.m. Let's have another great day with exceptional speakers and lively discussions. So the moderators, the floor is yours.
Sorry, quickly share. Iryna, do you want to pull up our slides? My computer was frozen seconds ago.
Absolutely. Here we go. Can you see the slides? Okay, Zhiting, do you want to start?
Sure. So welcome everybody. So today we are very excited to have a very strong panel. We have 7 distinguished panelists from academia and federal agencies. And so we are going to have the panelist presentations from 11 to 12:30 and 10 minutes each. And then we will have 12:30 to 1 p.m. as the gather time. After we come back at 1 p.m., we will break down to 3 sessions as we marked on the slide, and you will be able to join more in-depth discussions. So next slide, please. So we group the panelists in terms of their areas, and we will have them present in the order of their different subgroups. And so we will start with Professor Gang Chen. He is the Carl Richard Sobert Professor of Power Engineering in the Department of Mechanical Engineering at MIT, and Professor Pramod Reddy, Professor of Mechanical Engineering at University of Michigan. And then we will have Dr. Ravi Pressure, the Associate Lab Director at Lawrence Berkeley Lab, and Dr. Sven Mum from the Envelope Technology Office. He's a program manager there from DOE. And we have Master Bauer, the Technology Development Manager in Solar Energy Technology Office from DOE. Followed by that, we have Dr. Terry Hendricks, Program Manager from NASA JPL, and Dr. Peter Dubak, Program Manager at ARPA-E. So without further ado, let's hand the floor to our panelist, Professor Gang Chen, please.
Thank you, Zhiting. And let me share my slides. You see it? I assume you're seeing it.
Yes, we see it.
Okay. Good morning. And let me especially thank the organizers for your extraordinary effort at this extraordinary time. Now 2020 is in the past. I hope everybody have a safe and happy 2021 as it lightens up. And today I would like to share some thoughts on thermal energy related materials. And let me jump in first 2 slides, give a summary of some of the work we've done. And I want to actually get this one. Yep. So the point I want to make is the literature is not very generous with us in thermal materials, because the range of thermal conductivity, you can say at room temperature only 5 orders of magnitude. High temperature is smaller. But over the last 10 years, they're really exciting development in the materials. And I gave some examples from our own group, but there are really a lot of other work. So for example, the discovery of boron arsenate, first predicted by David Broidel using density function theory, and then several groups reported, including us, that has a thermal conductivity at room temperature 1200 watt-meter Kelvin. And cubic boron nitride reaches thermal conductivity 1600 watt per meter per Kelvin. And this is really filling the gap between copper and diamond, and really representing the best heat conductors beyond the diamond. And also, we can engineer polymers into materials, at least in the stretching direction, thermal conductivity as good as metal. And then reversely, we've been working a lot on engineering materials to have low thermal conductivity for thermoelectric application, like this left-hand side, silicon germanium super gallium arsenide, aluminum arsenide superlattice with nano dots. So I'm not going to talk more on this. We actually have a paper coming out of Nature Materials reviewing some of the development in thermal materials. And the next slide is really a summary of some of the fundamental understanding in the heat conduction. And of course, we build most of engineering system with Fourier law, pretty much all engineering systems. And we know over the last 3 decades, there are a lot of work on size effect, particularly Casimir regime. And really, last 10 years, there are new progress beyond the Casimir. For example, on the right-hand side, I show some examples, like a small dots heat conduction around it, we call it a more Lucent regime. And the recent discovery of photon hydrodynamic at a high temperature, the heat really propagates waves, and even heat conduction through Anderson localization. So this brings a lot of new ways to potentially control thermal heat conduction and go beyond the Fourier regime. And in a way, we can see if some people describe Fourier law as like a stone age of heat conduction, which is still very useful. But say we have come to an age where it's really, in terms of photon heat conduction, it's comparable to electron in the fundamental physical phenomenon, including quantized heat conduction. And that's all I want to say on the past work. And since this is an energy session, so I will just throw out a few personal view. What are the grand challenges? And I think number one is the storage. And on the left, you see the projection of increasing renewable penetration. By 2050, is about half of electricity generated by renewables. And the entire society will be more electrified. And the ratio here is electrical versus other energy usage. 2020 and 2050, you can see this ratio increasing. On the right, you see the PV price dropping, and then now it's some region is 2 cents even kilowatt hour, while coal generation is about 5 cents. And the bottom is the famous dot curve showing the power plant generation and in California, and you can see with the increase in PV alone, actually the power plant demand is very low, and sometimes the price is negative. But you need the spike in the evening. So the renewable storage is really the big challenge. Of course, people work on batteries for electric vehicle, but the battery is still a lot more too expensive for grid level storage. And this is where the thermal storage, I see great potential because the math, actually a simple math here. I can just think about using electricity from the PV to charge electrical, boiler, electrically heated boiler to a very high temperature. And if you think about the current power plant efficiency, coal-fired power plant is about 40 to 45% range. And if electricity price is 2 cents per kilowatt hour, you can make the stored electricity less than 5 cents per kilowatt hour. So there are people pursuing different approach. My colleague Ashigan Henry pursuing thermal photovoltaic. You probably heard from that from Pramod Reddy. And we thought about using this high temperature ready to couple to the boiler in current infrastructure using current power plant. But more increasingly, I thought that we could just use the concentrated solar thermal, the solar salt in the CSP power plant and coupled to just use that as the storage material for the current thermal power plant, coal-fired power plant. And there, the material, we want to improve this a little bit more. Rather than 565 limit, if we can work at the 650, because the ultra high pressure boiler could have run at a higher temperature. So there are corrosion issue, thermal mechanical problems, and measurement, all those, they're really the fundamental understanding of material at high temperature is direction, reliability we need to work on. The second challenge, I think, is easy to appreciate for this community, the efficiency. And we know that our current utilization of the energy input is less than 40%, or over 90% of the energy is input as heat. So there's really the efficiency in power conversion, the efficiency in utilization, and the efficiency in waste heat recovery. And you'll hear that probably from Rave and the building envelope, thermal insulation materials, regulation materials. And I worked a lot on thermoelectric over the last 20 years. And waste heat into electricity, it's a tough problem, right? And people always say there we waste 60% of the heat, and thermoelectric, other say energy converters. But the system efficiency has been low. And it turns out that you can think about the 5% probably thermoelectric energy conversion efficiency system, 5 to 10% maybe. And 5% seems low, but on the other hand, the photovoltaic is 20%, and the 6 hours. So if 24-hour waste heat, 5%, if you can make the system as low as price as photovoltaic, that should work. The problem is the heat exchanger. So we need to collect the heat and reject the heat. And that's more, expensive than photovoltaic. So this is where the plastic might be really a good direction, and then really reducing the cost. And my number 3 challenge, I think, is really the low global warming potential refrigerant. And there are some good progress in passive cooling. For example, this is Rongwei Yang's work on spectrally controlled plastic that can go passively read out the energy to the outer space at 3 Kelvin, so you don't need any energy to cool, or passive evaporator cooling, alternative refrigerant, and alternative ways to do refrigeration. And all those are related to materials. Let me use the rest of time to mention 2 opportunities I see. And one opportunity is actually use more electricity for heating and cooling. And even think about how we can use, say, direct heating for industrial process. I say this because if you look at the solar thermal, this is the International Energy Agency report, in 2009, solar thermal is 137 terawatt hour thermal energy. And 10 years later, it tripled. But photovoltaic here is 24 terawatt hour, and it's more than 30 times the increase. And the photovoltaic, say, well, I mentioned that some region is less than 2 cents per kilowatt hour. I remember solar thermal is about 3 cents kilowatt hour. So we can really think about rather than say long distance heat transfer, which is difficult, we know, electricity long distance is much easier. The other opportunity I saw is really the energy water nexus. You heard from my colleague John Linhart talk about the desalination and the wastewater. And I've been working with my colleague Evelyn Wang on atmospheric water harvesting, and also with Guihua Yu at UT Austin. And there's some really exciting materials like hydrogels and the MOF, metal organic framework, that could be used for this purpose. And also a lot of very puzzling fundamental side not understanding. For example, under solar evaporation, the evaporation latent heat seems to be only 1/3 of normal water latent heat. So there are a lot of fundamental understanding we still need to do in terms of absorption, in terms of the phase change. And with that, I'll stop here, and hopefully I'm within the time limit. Thank you.
Thank you very much, Gang. Let's transition to promote.
Right. Can you see my slides?
Yes.
Okay. Is it in full screen now? Let me see if I can.
Not a full screen yet.
Okay. Sure. Now it should be fine.
Yes.
All right. Thank you. Thanks everyone for the opportunity to present today, and thanks for all your efforts in reorganizing this meeting after the initial hiccups. So today I'm going to tell you a little bit about work or opportunities that exist in exploring the transport of electrons, phonons, and photons at the nanoscale. So let me begin by quickly providing some background, right? As Gang alluded to, in the last 20 years or so, people have explored the possibility of creating solid state heat engines via thermoelectrics, and significant efforts have gone into this direction. Okay, what have seen much less effort is in understanding some of the fundamentals of these processes in organic systems and in molecular systems. Okay, so let me provide a concrete example. Here is work, a theoretical work from 10 years ago or so, where people had suggested that one can make nanoscale or molecular scale heat engines, which operate basically at the Carnot limit or at the Curzon-Almond limit. The key idea is that by taking advantage of the rich variety of chemistry, one can create devices where the energy levels and so on can be tuned, for example, via quantum interferences, so that you can get desired transport properties. Okay. While these are interesting predictions, fundamentally the challenge has been in exploring this experimentally, right? So how do you take these single molecules and probe transport using them in those systems, and then learn the basic principles and later transition this to useful materials? So in my group and in collaboration with my colleague here at Germay-Hofer, what we have done is we have developed platforms which enable us to probe transport right to the atomic limit, right? So what we have, for example, done is develop very sensitive calorimeters, right? One of which is shown here, which is capable of detecting heat flows with, say, 100 picowatt resolution. And using these approaches, we have managed to trap single atoms or single molecules between these probes and looked at how heat flows in these systems, what new quantum phenomena arise even at room temperature in these systems, and so on. So that is with regards to heat flow at the atomic scale. Okay. So there is also a lot of interest in recent past in trying to understand how radiative heat transfer takes place in nanoscale gaps. For example, if you have like a hot object which is placed in close proximity to a cold object, then if the gap size is reduced to the nanoscale, you can have evanescent modes and surface modes contributing to thermal transport, which is expected to lead to dramatic increases in the heat flow rates. Okay. So what we have done is we've developed, again, calorimetric platforms, sensitive calorimetric platforms, and employed them to show for the first time that you can get approximately 1,000-fold enhancement over the black body limit by reducing the gap size between the emitter and receiver to nanoscale dimensions. Okay. So this clearly, I mean, this new phenomena clearly suggests that there is potential for using these ideas for energy conversion applications. And again, as Gang alluded to in his talk, thermophotovoltaic devices, right? So the question is, can you take a hot emitter, place it in close proximity to a photovoltaic cell, right? And a semiconductor device, and then reduce the gap size between them, and do you get essentially a lot more power output from the PV cell because of this nanoscale effect? So recently, what we have done is we have shown that indeed, by taking advantage of this nanoscale effects, you can get approximately 40-fold enhancement compared to the far field when you reduce the gap size to the nanoscale. Okay. So with this, I want to transition and talk about some of the opportunities in basic science and using them for energy conversion applications in the long term. Okay. So before I talk about some of the science questions, I want to highlight that one of the key things that is necessary to advance science is instrumentation. Right? For example, as I mentioned, calorimeters are central to probing a variety of heat transport phenomena, right? And if one analyzes the fundamental limit to calorimetric detection, you would see that, imagine a scenario where there is this region where heat is being dissipated. It is connected via thermal resistance to the ambient, which is a reservoir, right? It turns out once you use statistical mechanics, you can identify the fundamental limits to this, and you find that spontaneous fluctuation of heat between the reservoir and this region is what sets the fundamental limit to the smallest amount of heat you can detect, right? And if you were to plot this, as I show here, what you find is that at room temperature, in principle, one should be able to detect heat outputs as small as several femtowatts, okay? Whereas, as I pointed out, the resolution of some of the best tools available to us are around 100 picowatt right now. And if one were to able to push this limit to the fundamental limits that I described here, you should be able to observe a variety of phenomenon which can lead to groundbreaking breakthroughs. Okay? In fact, at this point, I would also like to point out that it is work on, for example, superconductor-based calorimetry that laid the foundation to some of the work that was later adopted using squids and quantum computing developments in recent years. Okay. So in the same line, people in recent years, in the last couple of years, have incorporated very sensitive thermometers into scanning probes and have managed to look at dissipation at single atoms in graphene and other devices. And one can, in principle, if you develop excellent room temperature thermometers, you should be able to do some of these things at higher temperatures. We have, in recent years, developed novel calorimeters in parallel with the group of Renkun Chen at UC San Diego to look at metabolism in biological systems, which by employing calorimeters which have around 100 picowatt kind of resolution, few hundred picowatt resolution. Okay. Again, development of calorimetry can lead to new insights into a variety of things, including energy and biology. Okay. So as I mentioned earlier, this nanoscale thermal radiation, for example, can be leveraged for energy conversion. And as I said, we did some of this initial demonstrations, but the efficiency of those devices were rather low, right? And there's been a lot of computational work, including this slide, which is from Gang's group, where people have argued that you can get relatively high efficiencies approaching 30–40% using near field thermophotovoltaics if you appropriately engineer emitters and PV cells and so on. And this is work that several groups are pursuing, including ourselves, and there is significant room there for development. So the last two slides, I want to highlight that there are several other new interesting ideas around now. For example, one idea which I think is very exciting is the possibility of creating photonic refrigerators. Right? So what has been speculated in the past is that, or theoretically proposed is that, by controlling the chemical potential of photons, it is in principle possible to build solid state refrigerators. This basically works by the idea that when you reverse bias an LED, the effective temperature of photons goes down. Okay, and this is covered in these papers that I cite here. And what we did very recently is to show that this is indeed true, and in fact, you can get cooling via photons if you cleverly design your system. And I think there is significant room for exploring these ideas in the coming years. Finally, one last opportunity is to understand systems which are very far from equilibrium, right? Where the distribution of electrons, holes, phonons, and so on is not described by one temperature because it is not in thermal equilibrium. There have been several suggestions that you can create plasmonic systems and so on, where you create hot carriers, which can be employed for catalysis and so on. But no tools exist for quantifying these distributions. So in recent years, or in the recent past, we have made some advances which enable careful characterization of these systems, but I think there is a lot of room for exploration here. So with that, I will stop and just highlight that there is room for a number of fundamental studies that involve thermal systems. Both thermal systems in equilibrium and non-equilibrium are far from equilibrium systems. Having said that, I'll stop here. Thank you.
Thank you, Pramod. And the next speaker is Ravi Prashar.
Can you see my screen?
Yes.
Okay, let me go to full mode. Okay, 1 second. Sorry, I'm having some issues here. Hold on.
It's in display settings if you change display setting.
Okay, let me actually just give me a second. Okay, you can. I'm assuming you can see it in screen mode now.
Yes.
Okay, thank you. First of all, let me say thank you to the organizers again, as other speakers have said. You guys have done an amazing job under this very testing time. In fact, I was fortunate enough to attend the last one, which was done in organized in University of Connecticut almost, I believe, 13 years ago or 14 years ago. That was a great experience for me. At that time, I was in the private sector. Again, and also thought, thank you for giving me this opportunity to share my thoughts. So I'm going to talk a bit about some of the fundamental and applied R&D challenges that I see in the area of thermal energy storage. Then I want to acknowledge Arun and Ashigan for some of the thoughts that I'm sharing here. Let me start with this. There is an urgency here. We all talk about it, but we sort of have quantified what is that urgency. This is an energy panel, and I believe that only reason we have this panel is because we have a climate change looming on our head. And that's the main goal. Otherwise, there's plenty of fossil energy available. So what I'm showing you here is that you have the CO2 emissions gigaton per year. And if you just do a linear fit and figure out what are the total cumulative emissions over the last 10 years, you come up with a very simple equation where T is the time. And then there is roughly 1,000 gigaton of CO2 headroom available to hit 2 degrees Celsius global temperature rise. Okay, so if you do the math, what you find out is we have roughly 20 years, right? So, and I think that's very, very important. I mean, as much as we want to talk about fundamental science related to energy, we cannot forget this timeline in mind, that we got to develop every idea with context to this timeline. And that should decide a lot of priorities when it comes to R&D related energy. So with that in mind, Arun, Ashigan and I recently wrote, at least what we felt are some of the top 5 problems in the area of thermal sciences for decarbonization. Thermal energy storage systems definitely top of the list. Decarbonizing industrial processes, cooling and heat pumping systems, long distance transmission of heat, and variable conductance building envelope. I will not touch upon any of these topics except the first one, but we believe that any advancement in any of these areas can lead to significant impact on overall energy systems. And in fact, I just want to point out that with the new administration coming in, I think we have seen some of the list of priorities in terms of technology areas they want to go after. And out of those 10 that I've seen, 3 of them are listed right here: storage, decarbonization of industrial processes, and cooling and heat pump systems. Okay, this is a graph which Gang already sort of showed. I'm just showing you a little differently, famously known as the duck curve. This is one data point, and now this is more of a common occurrence now in California. There was a particular day in 2017 where, as you can see, more than 50% of the electricity was coming from solar, which is a great deal. I mean, big deal, fantastic. However, the bottom graph shows you the cost. It's negative. So California had to give money to neighboring states to take the excess electricity away, right? Because otherwise the grid will become very, very unstable. And quite frankly, that's not a very scalable solution, that if the price drops to negative. And that's why energy storage becomes very important, because you generate most of the solar during the around noon or whatever, and then most of the energy use is later in the evening. And imagine if we had a storage. And now storage can be in 2 forms. Either you can store the electricity itself, which Gang talked about it, or you can also store the electricity on the demand side, which is for buildings is a lot of heating and cooling demand. So I will touch a little bit on the demand side of energy storage. And I think that's why we have this whole panel, 2 or 3 people talking about storage because of this particular problem. Okay, so some of the fundamental questions that I believe are very, very important. Modeling and prediction of latent heat of fusion. Okay, that's very critical if you want to talk about phase change materials. Modeling and prediction of subcooling is a nightmare, quite frankly, for room temperature thermal storage materials. I have never seen a single idea where people have not seen subcooling and directly affects the performance. Also, if you want to enhance the heat capacity of liquids, both as storage and just as a heat transfer fluid. And finally, can you tune the phase change temperature itself? Because for building application in particular, you need both heating and cooling. So can you tune the temperature so that it can store both heat and cold? I will not touch upon the last one, which I'm assuming maybe my colleague Sven may talk about it. Okay, so let's get into the first one, latent heat of fusion. So there is a very famous rule called Troughton's rule. And then there is a less famous rule called Richard's rule. What I'm showing you here is on the y-axis is the enthalpy of transition or enthalpy of melting or enthalpy of vaporization. And the x-axis is the temperature of vaporization or temperature of melting. And you plot this data and the slope is basically nothing but the entropy change at the phase change, right? And Troughton's rule basically says that to a large extent for vaporization, delta S is 10.5 times the gas constant. Richard's rule, there is a lot of scatter in the data, as you can see, but roughly it says 1.1 times R. And you do the math, you figure out that that's what it is, that latent heat of vaporization is roughly 10 times more than latent heat of melting. That is because entropy change is much, much larger, right? So now the question can be predicted, right? Is there a way we can predict this entropy change? And that prediction, if we can model it and predict it, then that will lead us to designing new molecules and systems for new phase change materials. So one other thing that we have been working on in my own group is how do we model it? So if you look at liquids, the potential energy surface is not like a simple harmonic potential that we are used to in a solid. It's much more complex, we should all know that. One is it's a rough potential energy surface. So you have this local minima, and then you have this, you can see the major shift. The major shift is basically the large scale diffusion of atoms or molecules. It's dramatic change in equilibrium position. The local one is basically a small perturbation around where the simple harmonic motion of atoms is happening. And you see the figure on the right hand side, where basically shows you that the local minima is that the equilibrium position itself is changing with time, okay? So you have small scale simple harmonic motion happening, except imagine that the origin of that simple harmonic motion is also shifting, right? So what we have done, and there's a lot of work has been done computationally using molecular dynamics for understanding primarily sort of diffusion and sort of viscosity and all those kind of things in liquids. So one of my students has been looking into it, that, okay, is there a way to use this idea to model, the enthalpy of melting? So what we are showing you here is a simple harmonic, motion, except we assume that x naught, which is the origin where the minima is, that itself is also oscillating. Okay, and I won't bother you with the math, but basically, if you do the math, and what we find out that the effective frequency reduces by a factor of 1 by square root of 2, and where omega dl is the Debye frequency in the liquid state, right at melting. Okay, and if so, that basically means that you reduce the frequency at the melt when you are in the liquid side by 1 by the square root of 2, and then once you do that and you do the math, what you find out is you can define right at melt what the delta S or the entropy of melting is. And it's a very simple equation, turns out to be. Only challenge there is that you have to calculate the Debye frequency in the liquid state, right at melt. One thing we have also assumed that right at melt, the large scale diffusion is negligible. And then I'm showing you the comparison of the Richards rule that I showed you. 1.1 R was empirical, but this is with a bunch of different monoatomic materials, and the match is fairly good. And similarly, we also explained now the Tauten's rule, except there is another frequency called the Frankel frequency, and Frankel frequency decides, the impact of the large scale diffusion on basically transverse phonons and stuff. So I won't bother with the details right now. But anyway, the idea is to show is that these kind of things are very important. These are very fundamental, but you can use a lot of these theories to really develop new materials potentially and get the right properties that we look for. Another major challenge is, as I mentioned, supercooling of phase change material is a major challenge. So what happens is that the material will melt at one temperature and then solidify at another temperature. And if you do the math, it has a direct impact on round trip energy efficiency of thermal storage, because you're going to get the energy at one temperature while you have to supply the energy at another temperature. So you have in that storage material, and it dramatically impacts the round trip efficiency, right? So the question is, how can we predict it, right? So in the lab, when we do DSC measurements, we are talking microliters, okay? When we go to applications, we are talking like multiple of liters, right? And so how do I get whatever data I get on DSC, and how do I know that the same subcooling and other performance is going to hold at that particular scale? And in fact, there is literature available already, which shows that people are seeing a huge discrepancy between a large scale system and whatever data they get from DSC. This is one data I'm showing you from a literature earlier. And so what are the fundamental challenges, right? We all know that fundamental understanding of supercooling metastability remains a grand challenge in science. And then there is this nucleation theory, but quite frankly, it lacks the predictive power for being to be very, very quantitative in nature. And when you look at supercooling, it depends on many factors: geometry, volume, material, microstructure. I mean, just name the number of variables there, right? So one other thing that we have been looking at is that if I do a very, very fast multiple measurements on a DSC tool, can I use statistics to predict the performance at very, very large scale? And we have had some really good success in that, where we have taken the material, doing the measurement at very small scale on DSC, and taken it to a very, very large scale system, and see how prediction happens. And there are two aspects to it. One is the volume changes. That means the overall number of nucleation sites are increasing if your volume is increasing, but then you have a counter effect of thermal gradient because of a finite thermal conductivity. So those two compete against each other, and that's what decides the final nucleation time, right? And the supercooling. Last one is as I mentioned, this dates back to my time when I was at Intel. We were trying to do microchannel cooling, and I was looking for new heat transfer fluids, which was beyond just a mixture of ethylene glycol and water. And I was amazed at that time, like almost 15 years ago, that development of liquid is almost like a black art. In fact, I visited a bunch of academic labs as well as a lot of the chemical companies. So anyway, one of the main reasons, as we know, water is really, really great, but 70% of the heat capacity of water is because hydrogen bonds are continuously breaking. And if you do the math of the bond energy and stuff, you find out that roughly 70% of the heat capacity is just coming from the bond breaking of hydrogen bonds. And then most of the other heat transfer liquids are van der Waals bonded, which have a lower heat capacity, right? So the question is, can we use covalent bond breaking to beat water or achieve higher heat capacity for T greater than 100 degrees Celsius, right? And that is where computational chemistry can become a very, very strong tool. And there is a massive advancement happening in that field, in the chemistry field. So a couple of students and a postdoc with a chemistry background, we started looking into this class of reaction called Diels order reaction, where you have basically a covalent bond. And what we found, the first experimental data that I'm showing you here started coming out, is that we have gone beyond 100 degrees Celsius and we are getting a significant boost in the heat capacity, right? Much more than mineral oil and other things that we are used to. And then now we are really looking into, can we even beat water? And the prediction, the deal, at least the DSC, sorry, the prediction from the first principles are showing that yes, it's maybe possible. So again, I'm just going to stop here, and we'll be looking forward to participating in the panel later.
Thank you, Ravi. The next speaker is Sven Mumme.
Great. Hello, everyone. Okay. So yeah, I'm in the building technology office. I manage both the building envelope as well as the thermal storage R&D. So in my presentation, I'll go over some of the opportunities and challenges I see for thermal energy storage in building applications, and provide a brief overview of the thermal storage R&D portfolio I oversee. So I'll go over some of these slides pretty quickly. As others have already articulated, the grid is changing from one that is one directional with centralized power plants to deliver power to end users to a 21st century grid that requires increased flexibilities, a new paradigm for energy use and storage to balance new and variable generation resources sources and increasingly diverse electric loads. So that's why you've seen a significant increase in the storage capacity over the years, and that is expected to significantly, why did it, sorry about that. Why is it, do you see it in full screen?
It's great, thank you.
Yeah, okay, not sure what happened there. So the thermal processes, heating and cooling make up a large portion of the building's overall energy consumption. Batteries have received much attention for distributed energy storage, but thermal storage can be uniquely suited to meet many of the building needs. As you can see in this figure, much of the peak demand in residential buildings is driven by heating and cooling loads. And if thermal storage can be used to shift some of the thermal demands to other times of the day, many utilities could more readily meet peak demands without infrastructure expansion. Thermal energy storage also holds the potential to have, significantly lower capital costs than batteries with longer lifetimes. So in the past, thermal storage consisted mainly of transporting ice to warmer climates. And today, we're a little bit more sophisticated with integrated systems to store, significant amounts of thermal storage on site. But in the future, we'll need technologies that are much more flexible, increasingly flexible, and with faster ramping. So the high energy density batteries we have today are a result of over 100 years of research and innovation. The scientific community has made a concerted effort to push batteries to greater heights. And as we look to develop improved thermal storage technologies, if we can glean and leverage any of the lessons learned from this long history of battery development, that would be really beneficial for this effort. And I'll talk a little bit more about why I think so. Most grid scale energy storage consists of pumped hydro storage, followed by compressed air storage. And these methods are really site-specific. Yet, the widespread development of distributed energy storage technologies like batteries is, currently still hampered by the high capital costs. So using the storage targets set by ARPA-E's grids program, the cost for storage per cycle would need to be around 2.5 cents per kilowatt hour or less. So here's a framework using battery storage as the benchmark. So we can use it to explore the challenges and opportunities that can yield breakthrough advancements in thermal storage, as well as help us better understand how component design and performance can impact overall system cost and value. So here are a few examples of how each of these parameters, capital cost, utilization, efficiency, and lifetime, can be articulated in terms of functions and properties for R&D exploration. I'll go into more details of all of these. Before I do that, here's our assessment, and take it with a grain of salt, but this is our current assessment of the state of the art or current state of thermal energy storage technologies, and none of the options currently meets all of our objectives for building applications. And we've developed, identified several areas needing improvement, which we mapped against the four overarching R&D goals I mentioned previously, to develop, improved technologies that would yield a compelling value proposition for building owners to reduce energy use and effectively shift and shed loads, and turn all of those circles on the previous slide to green. So let me go into each of these four areas. The first one being reducing capital costs. So many TES approaches tend to require large installations to achieve meaningful amounts of energy storage, and this leads to increased capital costs due to increased material requirements and needs, as well as system complexities, heat exchanger requirements, as well as the materials to house and insulate the storage medium. So to reduce the size and cost of storage installations, materials with both high energy and power densities are needed. And a potential path is to achieve is to look at designs for new materials and chemistries with high energy densities, as well as new heat exchanger designs and architectures for improved performance and lower cost. So next, I'll go into utilization of thermal energy storage in buildings and improving that. So this, as Ravi mentioned already, the phase transition of PCMs typically occur over a narrow band of temperatures, but in many building applications, PCMs are chosen for you have to choose a certain transition temperature to provide cooling or heating support. But in many in much of the U.S., there's both heating and cooling season. So, which means that there are many times of the year when the transition temperatures are suboptimal, which translates to, the storage medium not being fully utilized. And in fact, in most envelope applications in many climate zones and cities around the U.S., the utilization rate is far less than, you're actually using the storage capacity less than 50% of the time. So this utilization can be, improved significantly if the transition temperatures can be tuned over the course of the year in response to building needs, as well as another approach could be to a couple of thermal switches with thermal storage. There are many times in the year when there are favorable differences in ambient temperatures from inside and out. That if you could tap that, and it could help offset heating and cooling loads. So the introduction of thermal switches could really allow for an entirely new method of managing comforts and energy consumption within buildings, and take what is a traditionally static envelope to one that is an active contributor to energy usage and grid flexibility. So the next one is thermal energy storage efficiency. Now, as some of the other speakers have mentioned, there are a lot of thermal resistances and bridges that can increase the amount of electrical energy required to charge the storage medium, which reduces the energy and power delivery capacity of the thermal storage. So improved designs may be needed to really increase the overall round-trip efficiency, which can be done through optimized designs of heat exchangers to minimize the thermal resistance between the fluid streams, as well as reducing pressure drops across the device. So the last one I wanted to highlight is improving lifetimes. The longer the storage system lasts, the more useful charge and discharge cycles the owner will get out of the investment. So, while there are, thermal storage materials have their own degradation mechanisms, thermal storage materials are believed to be able to outlast battery systems. So if we find ways to increase the cyclability and reduce deterioration of thermal energy storage devices, it can significantly improve the economics of these technologies. One area of exploration is reduced phase segregation and improved encapsulation technologies for salt hydrates and other PCM classes of PCMs, as well as solid-to-solid phase change materials. So now I wanted to give you a brief overview of some of the activities we've been funding. So here's the the overall portfolio of thermal storage materials R&D. It does not include some of the systems engineering projects, but it covers salt hydrate and bio-based PCMs, as well as some additional classes of PCM materials development, thermochemical energy storage, enabling encapsulation technologies, as well as some of the cross-cutting projects exploring novel dynamic systems for enhanced energy savings that I mentioned before. So now I'll just quickly go over some examples. This is actually a compilation of at least 10 different materials development projects. One in particular that I'll just highlight is a project at Oak Ridge that is developing to reduce the, it's working to reduce the cost of thermal storage through, looking at salt hydrates in particular. And tackling the incongruent melting, large supercooling, low thermal conductivity, and corrosion challenges. So if successful, the project would lead to salt hydrate-based thermal energy storage with lower cost, longer life, and higher energy and power densities, and that really have the potential to be more cost-effective when compared to electric batteries. Sorry about my dogs. Someone just delivered. Okay, so this is one of the projects that wasn't in my overview slides. This is a systems development project where they're integrating high thermal conductivity PCMs with HVAC equipment. And utilizing the storage medium as a heat exchanger to provide grid flexibility, as well as increasing the COP and efficiency of the HVAC equipment. It also decouples the charging and discharging step of the thermal storage, providing enhanced utility. And lastly, this is a project that is jointly funded by us, the Buildings Technology Office, as well as the Vehicles and Solar Technology Offices, at NREL, looking at investigating the value of integrating behind the meter solar storage, flexible loads, and energy efficiency systems. And part of this effort, the Behind the Meter project, is exploring the use of thermal energy storage in buildings to mitigate the demand charges and to facilitate building-sided renewables and electric vehicle charging. They're also looking at an iterative framework that enables design, modeling, sizing, characterization, and evaluation of behind the meter thermal energy storage materials and components and systems. And its big objective is to minimize building energy costs and increase energy efficiency and maximize flexibility and minimize grid impacts of buildings. This is my last slide. These are some of the research questions that the project is hoping to explore and answer. Looking at hybrid systems, battery storage and thermal storage hybrid systems, and whether the combination of the two is greater than the sum of the parts. Looking at advanced characterizations, and can we glean and apply some of the correct characterization tools from the battery industry, and using those characterization tools to look at optimizing the configurations and architectures of storage materials and systems to optimize the power densities at any given energy density. So these are some of the questions that we're hoping to answer, and we've already gotten some good answers so far. Thank you.
Thank you, Sven. The next speaker is Matthew Bauer.
Hello and good morning, everyone. I greatly appreciate the opportunity to join you today to talk about the Concentrating Solar Power Program in DOE. My name is Matthew Bauer. I'm a technology manager for the team. And we're of course one of the two major solar technologies in our office, along with our photovoltaics group. I'm going to give an overview of the CSP system under the assumption that most people aren't highly familiar with it. And then I'm going to jump into both overall objectives for our programs, in particular some thermal energy storage challenges. So CSP, it's a dispatchable solar energy source due to the easy addition of thermal energy storage to our system. I like to say it's a glorified nuclear plant where our nuclear source just happens to be 100 million miles away, because after that, a lot of the subsystems are quite similar. You get your radiative energy into a heat transfer fluid. Then that heat transfer fluid can easily be stored without a major process. Then you want to transmit that energy into a traditional power cycle, a Carnot heat engine, and then go forth and provide electricity to the grid. Shown here are two common forms of CSP. The parabolic troughs on the left are kind of the most commercially mature form. And on the right is what's called a power tower, where you have a point focusing system getting light to a central receiver. Over the development history of CSP, I kind of like to denote this by 3 generations: oil-based troughs with a peak temperature around 400 C. Later, we evolved this heat transfer fluid called solar salt and incorporated it into power towers and got us to a maximum temperature of 565 C, and also could double as thermal energy storage is that same media. And more recently, our program has been working on what we call Gen 3 CSP, where we've been developing novel heat transport media, thermal energy storage, and everything that goes into that, associated with that, and pushing the temperature up above 700 C to increase the efficiency of our power cycle and ultimately get to a techno-economic goal that is cost competitive with natural gas and other grid energy providers. So I'd like to take just one slide to zoom in on the massive scope of our application. This is the Ivanpah power plant out in the desert in California. It's actually 3 power stations, really, almost 400 megawatts total power. There on the right, you see zoomed in on an illuminated central receiver. You can think of approximately 1,000 sun concentration ratio, so something like a megawatt per meter squared, blasting at that nominally 600 C skin temperature. And it's quite an interesting, we'll say, thermal transport problem of what dynamically occurs as the sun is moving, clouds pass, your heliostats target differently, your heat transfer fluid has varying properties to that system, possibly phase change. It's a very interesting glorified heat exchanger, really, where just one of your fluids is thermal radiation or solar radiation. One more image to emphasize the scale. Here's a molten salt storage tank, approximately 40 meters high. This one would contain nitrate salts at our Crescent Dunes plant, also I believe in Arizona. This grows several inches per day. It's an interesting materials challenge problem to cheaply maintain this potentially very cheap energy storage media for grid energy dispatchability. And also note that these kind of thermal storage vessels are the majority of thermal storage deployed worldwide today. It's the most commercially mature form of thermal storage. I want to think a little bit, I point you to think a little bit beyond just that typical CSP system of what are some other forms of what CSP could be. While not commercially mature, these are some things we thought about in a recent funding opportunity. The picture on the left is an idea where you take a typical power tower, like what I described, but you add some other indirect media that I intentionally made a black box here, and I called it indirect TES. And what this could be is a thermochemical reaction that might take 5% or so of your thermal energy in per day and does something. And that something provides some value proposition to the system. Hopefully it has some kind of a grid firming capability, because our ultimate goal, you can think of a normal CSP power plant, it might store energy to the day, then run overnight after the sun sets, and then turn off in the day when PV is cheap. But that's not what's going to replace peakers on the grid inherently. There has to be a guarantee that those 100 most in-demand hours of the day, there is energy available. And so that was the idea behind this kind of two-component thermal energy storage system. And on the right is something that I think is getting more and more talk regularly, but integrating with the CSP plant. And that's the idea of this Carnot battery, or even more simply, you can think of electrically heating, buying grid electricity to heat existing thermal energy storage infrastructure, or using a heat pump with a compressor. And you could append that to a CSP plant that has a lot of the infrastructure already built out. You could also, be more imaginative and think of doubling the power cycle as the heat pump cycle, and imagine round trip efficiencies from the grid in the order of 60 to 70%. So those are some forward-looking directions that we've eyed on, and I'm going to highlight a few projects that we recently launched in that vein of thermal energy storage. And I'll talk through these 5 projects rather briefly. Top left one is an idea nicknamed SoFuel, and that's from James Klausner at Michigan State, where he's thinking about having a solar thermochemical reactor. So at the receiver is a reactor of falling particles undergo an endothermic reaction to develop their fuel. And this fuel, they could sit at the plant for thermal energy storage at some later time to do the exothermic reaction, or you could put it on train carts and ship it to the Northeast and dispatch your energy there at some other power cycle, or use it for some other purpose. So when we talk, I think Ravi mentioned briefly the idea of transporting thermal energy. Well, this might be one of the simplest ways to think about creating high value thermal energy through thermochemical bonds and moving it to where it's needed. The next picture in the middle is NREL, Yang Zhao, working on higher temperature thermal storage tanks. Existing thermal storage salt is a nitrate salt with a max temperature around 560 C. And we've been targeting a chloride salt mix that's got with an operating temperature above 750 C, really. And this takes materials that can survive, that can be highly insulative, will survive the incredibly potentially corrosive environment, high thermal stresses, and still be very cheap and not destroy the pricing point that we want to hit with this system, which is ultimately around $15 per kilowatt hour. Moving all the way to the right is a rather complicated system developed by, or under proposal by Ellen Stechel of Arizona State. And this is the idea of process intensification, where we could take something that looks like a CSP plant, at some points run a thermochemical reaction with that energy to store energy for weekly or seasonal purposes. We could also buy energy from the grid to upgrade that thermochemical stored energy, potentially making hydrogen at off-grid hours, depending on the price the market wants to sell or buy electricity at. Lastly, on this slide, I'll run through these last 2 concepts. One is a simple bullet steam accumulator idea for process heat from a startup company called Sun Vapor. They're looking at using concentrated solar light in the food and beverage industry, but they need energy storage for the process. What do you do at low temperature? You find a very inexpensive way to store steam so you can have constant production of your thermal product. And the last one, it's a schematic of a system, but the point of this project by EcoGem is to explore the map for supercritical carbon dioxide compressors that could be either used in a power cycle or in a heat pump application to take electricity off the grid and put it into energy storage. Okay, so what is our program broadly about? At the most basic level, we target a 5 cent per kilowatt hour base load energy generation to put us on cost parity or better than natural gas prices. We estimate that due to the last generational shift in CSP technologies, we went from around 20 cents per kilowatt hour to around 10 cents per kilowatt hour in price. And the major thrust of our program right now is to make a series of generational advancements to get to that next major step and be a part of the energy conversation going in the future. While there is, several gigawatts of deployment worldwide due to the overall cost of the system, it's not significantly deployed this time. The plot on the right shows a study which there are significant sensitivities, but that indicates that if we achieve these price points, without any policy factors in place, there would be a very significant deployment of CSP in the United States, both in the Southwest. It actually happenstance a good deal of the Southeast also would be interested in CSP at these price points. And so we can take this top line goal and come up with techno-economic targets by subsystem. You can see I've called out thermal energy storage at the bottom with a high efficiency and a low cost per kilowatt hour thermal, and thinking about how all these ideas plug into a system. And a lot of what we fund in our program is focused work at developing components for subsystems or understanding fundamental science within subsystems that allows for R&D at more advanced stages. But we do want to think a lot more broadly than just the electricity sector. Most greenhouse gas is created not in the electrical sector, but in the thermal sector. And we've been thinking about a few other items. We've run desalination funding opportunities and have quite an active portfolio there. I'll highlight out of this group, though, the fuels and chemical production. And this idea of thinking about on this map on the bottom left, you see where the good direct normal radiance, which is the non-diffuse solar energy we want for a CSP application. It's not, of course, in the Southwest United States, and you see those black dots where our existing CSP plants are. If we, and kind of building off of that idea I pointed out from the SoFuel idea earlier, if we think of a world where we can create and run our chemical reaction of choice in the Southwest and distribute it to other parts of the country where the commodity or the energy is needed, it's a great opportunity for a tremendous effect for CSP beyond just directly making electricity. So with the brief time I have, and the last of my slides are going to kind of reinforce these points, I want to drive a few take-home messages for, I'll call it the tenets of CSP research and what needs to be done to be impactful for this application. The first point is that successful CSP research removes risk from a concept and drives to make a new solution reliable. A lot of times we're not doing the most basic fundamental science, although we do use quite a bit of freshly developed ideas from NSF and BES in our concepts. But we're looking at what risk remains. How robust is that solution? How broadly can I exploit it in what's going to be a dynamic application with lots of environmental facts that we can't tightly keep our pins on? The second tenet is that CSP components development efforts cannot de-risk through frequent iterations and numbering up arguments like PV, integrated circuits, and others. This has been probably one of the challenges that why big thermal systems are slower to develop. We don't get trial and error. We have to think very carefully about the risks of scaling up these systems before we can make $300 million pilot plants or whatnot. The capital to try something that's relatively mature is quite high. And then the last point is that advanced CSP R&D lives at high temperatures where chemical kinetics and thermal stress drive to rapid failure. So reinforcing these ideas of risk mitigation and not having access to allowing things to fail when they will fail quite rapidly at these high temperatures. So to give some perspective to that first point, this was an exercise I went through where I was thinking about why a novel solar receiver might not work. And I just went through, quickly jotted down the risks of one specific concept and the completeness of the approach that it takes to get somewhere. So unlike other systems where, unlike the electronic world where thermal problems are a byproduct that is unwanted, here it's all about the first order problem is getting a high thermal efficiency, high control of our thermal flux, exploiting phenomena to get that into our heat transfer fluid and storage in a way that doesn't increase our cost through losses. But even if we overcome that hurdle, there's a litany of challenges that we have to think about how to solve in tandem with maintaining our high thermal transport. And that's a lot of times the death knell to lots of very attractive approaches to improving subcomponents. And I'm going to give a quick example of, what does that mean to someone doing a kind of more basic research project? And I'll highlight a project from my colleague Shannon Yee and one of his colleagues, Andre Gunawan at Georgia Tech. And the project, it's kind of straightforward. It's taking two techniques. One is a more advanced laser flash tool, and one is a home developed or lab developed 3 omega approach to look specifically at high temperature properties of both fluids and solid material for our application that haven't been studied at those temperature regimes. And it's not just about collecting the data points. I like to think of this in the FAIR principles approach. And FAIR principles stands for findable, accessible, interoperable, and reusable. And it really has to do with big data, is why that concept was created. But the point to take from that is, what do you do to create a data set that doesn't just support the theory that you want to write about in a specific paper, but that can truly be built upon in a way that someone who has $100 million investments can rely on it, that the research community doesn't feel the need to go remeasure points countless times, and allow us to step forward. Because this is what we need if we want to rapidly move forward in the time frames that we have to avoid major global warming impacts. To the second point of those tenets I brought up, I want to highlight, and the font got a little off here, the depth of the research problem. And that is that we need to be thinking large, even when we're studying at the small scale. We need to be thinking about how the risks that I haven't been able to think about or study in my 10 kilowatt system are going to manifest later on, and what I can do early on in the research to get us something that is more applicable at the pilot scale. The worst thing in the world is when you're ready to build a demo and you realize basic problems aren't really answered because they just didn't have to be incorporated in the studies that were happening at the small scale. My colleague Michael Ohadi talked a bit about the SCO2 Brayton cycle earlier. I won't spend a lot of time here. I'll just say that this
1 minute, please.
This is something that we are very interested in and exploiting at higher temperatures. And we develop our systems a lot thinking that this will be the future. We recently invested about $40 million into a 5 megawatt demonstration of this system in a complete CSP plant with Heliogen as a lead entity. And the last bit I'll talk about is the Gen 3 CSP program. This is our program where we've had several teams compete to develop an integrated thermal transport system at higher temperatures, nominally a 720C outlet temperature, that's included innovations in the receiver, the storage, heat exchanger, pumping cycle, or transport. And we've looked really closely at chloride salts, sodium materials, sand materials, and other particle transport media throughout this system. And I think we're going to have a lot of really exciting information come from this program over the next couple of months. I'll give a few other final examples of work that we've done. This is something I'll highlight from my colleague Rinkun Chen, who's worked on this Gen 3 program. And this is an in operando method for measuring dynamic thermal transport in an active system, which I think is really interesting. It's a pump probe type technique, but it's a photothermal radiometry rather than maybe reflectance that more people are used to. And it works beautifully because the signal to noise ratio decreases with temperatures. You get this opportunity to probe from the outside of a pipe what may be happening in dynamic properties as you don't fully understand perhaps particle flow on the inside, or if you have a salt flowing and you put in a metallic getter and there's some dynamic heat transport properties to understand in real-time events, or even perhaps study a receiver in operation. I'm going to skip these slides this time. This is just a summary of some of the different receiver research we've been doing. And I'll close with this. If you want to know what our program is doing most in the very near term, these are some of the workshop events we've been holding. The summary is available online. I'm glad to talk to people about these topics more further. But some of the ones I'll highlight is the second point, next generation receivers. We're very much thinking about how to develop high impact receivers with a very long view for high value applications. And we're very much thinking about that, not just as receivers, but as thermochemical reactors going forward, and what are the high value, perhaps direct or indirect solar chemical reactions to develop technologies for, as well as this idea of pump thermal energy storage or Carnot battery, potentially integrating with CSP plants to increase the value of proposition. Thank you for your time.
Thank you, Matthew. We have to move to the next presentation real quick. Terry, you're able to share your slides?
Yes.
All right, the floor is yours.
Okay, thank you. Let me get these up and going. Okay, can everyone see that screen now?
Yeah, yes, and if you want to put it in presentation mode, I think we can see it.
Okay, there we go.
Excellent.
Okay, so first of all, I'd like to thank the organizers for this opportunity to talk with you today, and also their amazing efforts to get this workshop, virtual workshop in place. So I'm going to talk to you about some of the new potential mission concepts that we're working on at JPL. The first one is, which represents a very major new frontier for us, is that of cryohydro robots for ocean worlds exploration. And we are in the midst of designing some very sophisticated ice penetration robots for penetrating the ice layers of Europa and Enceladus and getting to the ocean ice interface. These are very sophisticated systems. It's a major thermal problem. It's probably the toughest thermal problem in the solar system besides going to the sun, as it turns out. We are incorporating 8 to 9 kilowatts of radioisotope thermoelectric power systems in this design, as well as several different passive and active thermal systems to allow us to get through the ice layers. The ice layers on Europa and Enceladus are anywhere from 10 kilometers to 40 kilometers thick. And so it will take us anywhere from 2 to 3 years to go through those layers and get to that ocean ice interface. The whole thing we're doing here is looking for signs of life and biological processes at these ocean ice interfaces. The stages of ice penetration, there's many, several different stages. It represents one of the most extreme environments that we have to deal with from a thermal standpoint. The ice is very hard, it's very cold, approximately 100 Kelvin. And the pressures can be very high in some of the deeper regions, upwards of 54 megapascals. And the environment also has a small amount of corrosive components and constituents in it as well. So this is a very major area that we're going to be working on going forward. The other area is in the second frontier. As many of you may know, we are looking to go back to the moon. And so we are looking for several technologies there, combined heat and power systems for lunar surface operations. There's significant interest in new chemical heat and power technologies. And these would be chemically driven systems. I'll talk about that more in the next slide, but we are trying to circumvent the use of radioisotope power systems because their use is challenging given budget and cadence of some of the missions to the lunar surface. Lithium-ion batteries are mass prohibitive, and so we are looking for other ways to develop heat and power systems for long-term operation on the lunar surface. This current system we're developing is called CHIPS, and it's a combination of a high-temperature chemical reaction system that utilizes a very high energy content exothermic reaction to provide the thermal energy. That energy is then picked up by sodium heat pipes that transfer the energy from our chemical reactor system to a couple of places. One is, first of all, a thermal to electric conversion system, or to create power, and also directly to a lander system to help create, to warm the lander systems and allow them to survive lunar nights. Our whole goal here is to be able to provide not only thermal energy to keep the systems warm, but also to provide, simultaneously provide a amount of electrical energy to the lander to keep it operational. We have looked at things like Stirling converters and thermoelectric modules for doing this. We have at the moment chosen Stirling converters to do this because they're much more, gave us much more capability. The remainder of the thermal energy that comes off the Stirling system will then be transferred to the lander as well to help keep it warm. So we have two thermal pathways to keep a lander warm and at the same time providing electrical power. Another major challenge in returning to the moon is that of dealing with the lunar dust and lunar dust adhesion to every surface you can imagine. It can get when you're working in lunar dust, it's akin to working in sort of talcum powder. It gets on every surface: environmental suits, sensing optical systems, solar arrays, thermal radiators. It gets on excavating equipment, power distribution equipment, and it's just a major issue that has to be dealt with. So that is one very big challenge in returning to the moon, especially if you want to stay there for a week or weeks, a month at a time, for instance. This is going to be a very big challenge to deal with going forward. Coming back down to the earth a little bit on how some of this technology could be used in the United States and our energy flow. This is a common chart that people have seen in the past. You can see that this is a flow chart of how energy flows from our energy sources all the way to our use within the country. And the main thing over here on the right-hand side is the amount of waste heat that could be harvested. In 2019, it was approximately 67.5 quads. That's up from about 8 quads, up by 8 quads from 2014. So that's a big opportunity there. There are a number of technologies that we are looking at, and these include thermoacoustic energy conversion systems to recover and utilize this energy, Stirling systems, Brayton systems, organic Rankine cycle systems, and thermoelectric systems. Terrestrial energy recovery is needed in many terrestrial applications, as we know. First of all, the most recent developing area is in aircraft energy recovery, also industrial energy recovery, marine, and automotive. We have, oops, all right. Oh, there we go. One recent program that we have ongoing with GRC and JPL is the recovery of energy in aircraft and aircraft engines. There's about there's hundreds of kilowatts of thermal energy available in aircraft engines that's available for energy recovery. We are looking at a combination of thermoacoustic tube energy conversion and advanced thermal capture, heat pipe technology, heat exchangers to capture this energy and move it around an aircraft to provide enhanced power generation and cooling on the aircraft. In the area of terrestrial energy recovery, we're using at JPL, we're using some of our key advances in high performance heat exchangers and our advances in high power flux thermoelectrics to help address these needs. We are developing high temperature thermal heat exchangers to address the needs not only in the aircraft industry, but in industrial energy recovery. We've seen in the past that TEG systems have been used in automotive applications. However, the whole issue there is it's all about cost. And one of the most recent pieces of work that I've been involved in is looking at the impact of various design parameters on driving down thermoelectric system cost. And the two major things that seem to drive it the most are not only the hot side heat flux at the hot side of the thermoelectric, but also the cost of the heat exchangers themselves. And this plot here shows you how you can actually affect and create a much larger reduction in TEG system costs by increasing the heat flux by a factor of 4 than by decreasing TE material costs or TE material manufacturing costs by a factor of 5. And this is one of the latest changes, paradigm changes that has come about, and it represents a new frontier because the thermoelectric community has to completely change its view of how to approach this. It is not all about thermoelectric materials. The thing that can, it turns out that the thing that can drive costs in bigger steps and bigger increments are the heat exchangers themselves. And this goes along with the work that's going on that Mike Ohadi is leading up at RPE and the high temp program, and other programs that are also addressing the need for low cost heat exchange systems.
1 minute, please.
Yes, okay. The final area is we are heavily involved in thermal control for deep space, small spacecraft cooling systems. We are focusing on two-phase pumped loop systems. And this here shows a picture and a schematic of how that goes together. We've got a lot of subscale testing capability at JPL that we're using to address this. And as part of this work, we are addressing and utilizing additive manufacturing to build and fabricate monolithic 3D printed evaporators, condensers, wicking, porous material, wicking materials. This represents for us another, the final frontier for us, number 5, in the use of additive manufacturing to create very complicated and very functionally graded materials that have a lot of capability and robustness in their design. With the needs we have here are to be able to do this do additive manufacturing with a wider array of materials, and also to be able to quantify the changes in thermal properties and structural properties of materials that from their bulk state when we do additive manufacturing. So I will stop there. That is sort of a snapshot of some of the key frontiers we see coming up at NASA JPL.
Thank you, Terry. And we'll have a chance to discuss it more in the breakout. Peter, are you ready?
Yes, let me get the screen started. I'm going to start with the beginning, not the end. Thank you, everyone. I really want to thank the organizers and NSF for setting up this so far excellent series of meetings. A lot can happen in 1 year. I remember this last year being on the front of one of the first conferences that was canceled because of COVID, and thank God we're all safe. A lot can happen in a year. People can also change roles. So I changed role and became an RPE program director in the last year, and have recently started looking in the areas of hybrid propulsion and energy consumption of electrical systems. I'll go over these slides a little shorter because we heard a lot of this message already from the prior speakers. We did an excellent job in communicating this. But besides just the temporal offset and also geographical offset of energy production and demand, where we used to have locally very large power plants, now distributed power plants, we also have an additional challenge in the flavor of electricity, where we're looking now at DC at different voltages coming out versus prior industries really used large motors. So there's a lot of focus on power factor and electrical machines. New applications that actually demand electricity now are electric cars, data centers, and those kind of applications are not only are also changing how we should look at the grid. So it's not just the supply side, it's also the demand side that has changed dramatically. One fun math I did once is if you're at the pump fueling up your car and you have about 12 gallons of gas going into your car in 3 minutes, you're actually transporting 9 megawatts through your hand. That's quite an incredible energy load that a chemical carrier can transport. And of course, electric cars are more efficient and you can take a little bit more time, and therefore it's feasible for electric vehicle transportation to become electric. And that in itself has a tremendous effect already on the CO2 emissions, but how can we bring that further? Now, the same does not hold for aviation. Electrifying or making aviation emissions, reducing those significantly, is a lot more challenging. And I've got a few slides that I put together on that particular topic. I'd like to ask your attention to the chart in the bottom left, where you see, I think, a very historic change for somewhere around 2016, 2017. The transportation sector overtook the power sector as the main emitter of CO2 emissions. And we heard from Ravi the urgency of how as a society we need to think about these emissions and reduce those. Now, of course, we have electric vehicles come in. There are other sectors of the transportation spectrum that at the moment are not on a path for electrification yet. And maybe this is an area where organizations like RPE can help. Just to do that same kind of trivia question that we had for the car fuel transmission. If you do the same for an airplane, it looks a little bit differently. An airplane at the gate can actually take on about 1,000 gallons per minute of kerosene. That's quite a lot. Sometimes actually twice that much, because there's one, if the gate has two particular, they call them little hydrants. If you do the electrical equivalent of those kind of chemical transfer rates, we're looking at 2 gigawatts per aircraft, per gate, and sometimes maybe 2 per aircraft. An aircraft, a large aircraft like a 747, would be on a fuel hose like that for about 50 minutes. So the amount of energy going into aviation is extreme. If you would like to do that with electricity transfer, which is, the transfer of electricity is often underlooked compared to the battery question. You would need to have a power plant the size of a nuclear power plant at each gate, which is a very challenging proposition. Of course, maybe it can be more efficient. The second challenge is if you do need to store that energy on an aircraft, if you'd like to do it with batteries like you do with vehicles, you have a problem in the storage density. In an aircraft, about half the weight of a fully loaded aircraft, wide-body aircraft, is fuel. So when you fly, you burn 90% of that fuel. Even if the batteries would have the same density, you'd have to throw the discharge batteries out the window, which we wouldn't want to do, to get the same range out of the aircraft. So aircraft are really focused on power density. That's the key metric for everything on a propulsion system for an airborne system. So what this means is that if we look forward to how to reduce emissions of the aviation sector, we probably have to use some kind of liquid fuel. And if we do use a liquid fuel, maybe we can get a carbon neutral liquid fuel. And carbon neutral liquid fuels are those that we grow by pulling emissions out of the air, such as bioethanol, biodiesel. There are also synthetic processes. And this is, I think, a very key area as the aviation sector is trying to become green. And the second thing is, if you do use a liquid fuel, let's try to use it as efficiently as possible. Because currently, we saw the example just from Terry, where he says there's still a lot of waste heat coming out of an engine, and he's correct. There is a lot. And RPE has, before me arriving at RPE, so already had shared the same vision and launched these great programs called Reach and Ascent, which together are planning to take the efficiency of an airborne propulsion system from about 34% to 60% or greater. Reach focuses on a range extender that can take a carbon neutral fuel and transform it into electricity. And Ascent will focus on taking the electricity and making very efficient, compact motors, as well as cooling systems, as well as power conversion, and turning that into shaft power. And just to give you an estimate of some of these, of the goals of these programs, is some of the best-in-class electric motors right now are about 5 kilowatts per kilogram. Ascent will push this to 20 kilowatts per kilogram. And by also including the whole system aspect, the thermal management system, as well as the power conversion, the whole system is targeting about 12 kilowatts per kilogram. So it's a significant leap forward. Now you can see that these two core areas of an aviation propulsion systems are being worked. There are still areas that are open, and that's areas where we'd like to actually hear more from you about. So carbon neutral fuels, how do we get electrical energy or other waste heat, other mechanisms? How do we produce about 90 billion gallons of carbon neutral fuels? Because that's what the aviation industry uses. Second, the electricity transport is already being worked a little bit with our high voltage at high altitude or cables program. But there are maybe other ideas there as well that could be interesting. And then last, on the propulsor side, how do we turn shaft power into aviation propulsion and even greater efficiency than we have right now? Right now, we estimate that it can be done around 80%. We'd like to get to 90% with that as well. So I'll try to summarize a little bit what I think are the grand challenges. So energy storage was mentioned a lot. I think it's a key area for our generation, and it's a really exciting time to be an engineer in the sciences, because there's so much great work to do. if you look at the amounts of changes that have occurred in the last decades, it's amazing. The solar, there are some charts where you see the amount of energy from solar displacing basically coal and other plants. It's quite impressive. But we need to be able to manage those loads, both from a supply and demand side, to work on technologies like both thermal and electrical storage. Batteries, energy transport. So another way to manage loads is to transport it from one way to another. But also, I really appreciated Ravi mentioning thermal fluids. I think this is an area where there's a lot of opportunity, where we've seen the materials community now using these computational tools to develop new materials. I would love to see similar efforts on the thermal fluid side. If you look at what do we use for cooling, it's water, it's propylene glycol, it's air, it's a bunch of oils, R134. If you look at these properties, especially for phase change, supercritical fluids can be very interesting as well. And I'm not sure whether to call it a phase change or not, but if you go from liquid to supercritical state, there's an enthalpy change there. And I did this once for CO2, and that enthalpy change that occurs from liquid to supercritical is equivalent to R134 evaporating. So can those kind of fluids be used for thermal transfer, maybe even thermal storage? I mentioned the topic below, renewable liquid fuels, electricity to fuel. Would be a Nobel Prize kind of invention. I'll wrap up. And then efficiency of new industries. I recently launched a webcast on some of the new high energy usage industries that I think we can make more efficient. I have some of these elements summarized here. Propulsion concepts would be really interesting to learn more about. Supercritical cycles for heat and power generation. And if I look at the third bullet here, superconducting compact cryocoolers, it'd be great just to explore Professor Reddy's ideas of photo refrigeration would be very interesting, as well as I would love the thermoelectric community that has a great understanding of phonon transfer to also explore the electrical equivalent of a heat pipe. How can we get the conductivity of copper and the electrical front even higher? This would be very exciting to see going forward. So I hope these thoughts stimulate some great work. I want to thank the organizers for this workshop.